Okay, we should be live. It's very rudimentary because I haven't prepared it yet, and I can't change the title, so it's still quantum entanglement, but we are live.
Okay. All right. Well, let me just start then. Welcome to Physics number 103, streaming live on YouTube. Shamash will put a link in the chat soon if anybody wants to. That's a nice way to be able to watch and not be here. Although we love having you here because it makes us feel like we have a full room. This is, yeah, number 103 in the Physics series. And we're going to talk today about eclipses. A lot of stuff that I think most everybody kind of knows, but not bad review. And we'll get a little more quantitative about things and kind of point out a few things that maybe are not so well known. This came up as a lot of my bites of physics do. It's a result of my discussions with flat earthers who, and in particular, as we'll talk about, a very real question about which way solar eclipses cross the face of the Earth. I'll just put that out there right now. It's not immediately obvious whether solar eclipses should run east to west or west to east. You, anybody want to? Well, I don't know if anybody wants to say anything about that. You're welcome to unmute, but we'll
I'm not
we'll
sure what do you mean running from east to west or west to east. I'm not sure what you mean.
well, the path of a solar eclipse crosses the face of the Earth generally, and there are exceptions that are not real exceptions. I'll put it that way. Maybe we'll talk about that later on too. But they do run west to east. Eclipses start if they cross America. They start in the Pacific Ocean, cross America, and end up in the Atlantic Ocean. Typically, they have different paths, but east to west is the direction they move. And it's not immediately obvious that they should do that for several really good reasons, and that's what brought this up.
East
Go
to
ahead,
west or
Andy.
east to west or west to east?
What did I say? Did I say east to
You just
west?
you just said east to west.
Oh, okay. Sorry, that was wrong. I misspoke. West to east. Thank you.
Okay. The
Yeah.
only reason I even have a thought on that is because the last big one that went through North America, what started in Mexico and went through Texas and kind of continued its way northeast. And without that memory, I would have no guess
Yeah.
what it did.
Yeah, that's right. In fact, I had kind of the same thing at first. When the question came up, I kind of convinced myself at first that they should go east to west. And then I thought about an eclipse I saw and I thought, yeah, I think that did go east to west. I kind of convinced myself that it had. The one solar eclipse that I saw was in Wyoming back in 1980, I think. Might have been 79 or 80. And I kind of managed to convince myself that it had gone east to west, but I was wrong about that. Anyway, we'll get into all of that stuff as well. Let's maybe without further ado, if you open up the slideshow at the top there, you can follow along with the slides as always. So we're doing eclipses. If you go right away to slide 2, just the simple kind of geometry. We're going to talk about solar and lunar eclipses. We're not going to spend much time on lunar eclipses. They're not quite as interesting for a couple of reasons. Not quite as rare, and they're not nearly as spectacular, of course. But the basic actors, of course, are the sun and the earth and the moon. And so the orbits are kind of showing the orbits here, showing the tilts of those orbits. Everything, if you look down on the solar system, with some exceptions, things tend to, almost everything rotates counterclockwise. If you look down, I should have put that in quotes too, looking down from the quote top or the north. I often wonder how Australians and people in the southern hemisphere, if I think they might have a little more of a difficult time, even though they're not standing on their heads. Or in fact, I think they might have a little more difficult time dealing with talks like this and information about the solar system because they're not standing on their heads. Because all of this really makes a lot more sense standing the way we do in the northern hemisphere and kind of looking at it, an angle, looking down. I always wonder if Australians have a little more trouble because they have to kind of go through one more contortion. Maybe it would be better if they were standing on their heads. Anyway, these pictures are typical, right? They're kind of slanting down, looking from above, counterclockwise rotation, very northern hemisphere centric kinds of things. It's too bad because northern hemisphere centric stuff means we've got to say counterclockwise. If it were the other way around, everything would be going clockwise, and that would be kind of nice, have its own little advantages. But these pictures on slide 2 are really out of scale, as we'll see in a minute. Just kind of intended to show that things are tilted, things are rotating counterclockwise, looking down. If you go to slide 3, get a little more information. It's a little more to scale. The Earth's, the distances are a little bigger compared to the sizes. Not nearly to scale yet. These sizes are way too big. You wouldn't be able to really make out any of these objects except maybe the sun as a tiny little dot at this kind of scale. But this picture on slide 3 is intended to show that that the moon's orbit is tilted relative to the Earth's orbit around the sun. And that means that in the two positions shown at the sides, on the right and the left, there could never be an eclipse. Right, when the moon passes in front of the Earth, its shadow doesn't hit the Earth, and vice versa. When the moon is on the other side of the Earth's shadow doesn't hit the moon. So there can be no lunar eclipses, no solar eclipses in either of those positions. You have to wait 3 months from one of those positions to get into either of the positions shown at the top and the bottom, where the sun and the Earth and the moon are in alignment because of the tilt of the orbits. That so-called line of nodes is the place where you can get eclipses. And so this is why there are eclipse seasons that are 6 months apart. If you have an eclipse of the sun or the moon at some point, then you won't have another one for at least 6 months. And typically, there's always an eclipse. Every eclipse season, there's some eclipse. Almost, I think, always a lunar eclipse, and quite often a solar eclipse in an eclipse season. But sometimes an eclipse orientation doesn't generate a solar eclipse because it has to happen within a few weeks of the right orientation, or else the tilt gets too big again. Now that might bring up the question, if that's the case, if there's only eclipses every 6 months, why don't we know that? Why don't we know that eclipses only happen in July and January, for instance? And that's because they don't. And that's because over the course of 20 years, the orientation of this tilt goes through a full 360-degree wobble. So 5 years from now, it will have wobbled through to make the eclipses on the sides here. The orientation of the moon's orbit will be such as to make the eclipse season be the side-to-side positions rather than the up and down positions in this diagram on page 3. And then another 5 years later, it'll be back to this kind of a season with the tilt being the opposite way. The tilt, rather than going kind of from upper left to lower right, will go from lower left to upper right, but you'll get the same eclipse season. And the whole thing cycles about every 20 years. So we do get eclipses at all times of the year, but at any given, if you see in some given year, you see eclipses in March, then there will not be eclipses in any other month except September. They'll be basically 6 months apart. Okay, any comments or questions before we go on? Oh, let's get Richard up here on the stage, if we haven't already. Hey, Richard, did you come up just to hang with the cool kids, or do you want to say something?
Yeah, hanging with the cool kids for sure. And I will have some questions later. I've invited my astronomy group, the Astronomy Association of Jamaica, to join. So I've
Oh,
just sent
great.
them the link online. Thanks.
Excellent. Thank you. Okay. Let's see. So let's move on then to slide. Where were we? Slide 4, where it's a little aside on this notion of scale, as I said before. So here's a scale model picture of the Earth and the Sun. That distance, of course, is I'll do astronomer speak here. That distance is 100 million miles. It's nice just to think of it 100. It's a little more than it's not. It's a little less than that, 93 million miles, but something like 100 million miles. And on that scale, to get that 100 million mile scale on the page, I had to make the sun the size that it is there. It's just 1% of that 100 million miles. I would have to put 100 of those little orange suns in a line to make it from the sun to the earth. And on this scale, the Earth, which is 100 times smaller than the Sun, I can't even begin to show you. I've just got two lines going from the place where the Earth is to the top and the bottom of the sun there. And that angle that you get when you draw a line from the Earth to the top of the sun and another line to the bottom, or of course, any two diametrically opposite sides of the sun, subtends, geometry talk, a half a degree. That angle that I'm showing you there is a half of a degree. And that's a really ubiquitous angle, strangely enough, in astronomy. It's really a nice angle to remember because it represents something at some size, something of any size held 100 times its size away from you. That's not exactly right, but once again, it's close enough for our purposes. If you take an object, a penny, and hold it 100 penny diameters away from you, that'll be a half a degree. And you won't be able to do that. You won't be able to hold a penny 100 pennies away from you. You'll have to have somebody else do it for you because your arm isn't long enough to do that. But when you do that, you can hold it up and it will just cover the sun. And it will just cover the moon because the moon is also a half a degree. It's 400 times closer than the sun, but it's also 400 times smaller. Once again, those are astronomy speak numbers. It's not exactly 400, but those are nice numbers to remember. It's a quarter of a million miles, and the sun is 100 million miles away. So that's a half a degree there. And I put this slide together for another purpose. But another place that half a degree shows up is kind of the maximum amount that a light ray ever curves going through the Earth's atmosphere when we see the sun setting at night. We see it for about 4 minutes longer. 2 minutes longer. Approximately 2 minutes, depending if it goes straight down. About 2 minutes longer than it's actually physically visible. We see it when it's just a little below the horizon because light from the sun curves downward, and as a result, it can kind of curve around the horizon into our eye. In doing that, it curves by about a half a degree. And so I'm showing you a red line there. If you actually took this, that line really is curved. I made it curve by about a half a degree. So the direction it's moving at one end, it changes that direction by a half a degree by the time it gets to the other end. And that's the most any ray of light curves. But I should point out that to do that, light doesn't travel, 10 centimeters or 20 centimeters as it is on this slide. It actually, in order to do that, it has to travel hundreds of miles. So the curvature, if you can see the curvature of that line, that's hundreds and hundreds, sorry, not hundreds, millions of times more curvy than light actually is going through the atmosphere. It barely curves at all. You would never notice that it's curving to look at it, but we do in the sense that it lifts that image. So that's a little business about scale and the idea of half a degree. Half a degree is really a nice angle. something 100 times further away than it is wide is half a degree, and that's what the sun is, and that's what the moon is from the Earth. So all those things are nice. Any comments or questions there? Let's see what's going on. We've got. Oh, the cool kids. Yeah, always so much wants to point out the cool kids are in the audience. That is true. I find that a lot when I go into Discord rooms. Discord, I go into too many Discord flat earth rooms, and there I guarantee you that the cool kids are not on stage. They're sniping down in the audience. So consider yourselves cool if you don't come up. And if anybody wants to leave the stage, you can do that and consider yourself cool too. Okay,
No,
let's
I
move.
want to be
Go
boring.
ahead. Hi, Shamash.
If you have, if you're looking at the sky and you want to determine that some sort of object is half a degree, then you can take the sun as a reference for that.
Yeah, don't do that's probably a bad idea, but go ahead.
No. My question would be that's still too big. Like if you were gonna look at everything else in the sky, it would be way too small to apply that kind of scale to it.
Yeah, it's really our ability to judge angular sizes is so bad that when you want to kind of do things like that, what you really want to do are take pictures and kind of count pixels and have something in the picture to. I do a lot of that. It's really fun to take anytime you get a picture with a moon or a sun in it. That moon or that sun establishes the angular scale of the picture, and you can do all sorts of fun things by knowing what a half a degree looks like in that picture. Otherwise, of course, you can't know. You can't know what focal length was used. You can't know if it's been cropped. You can't know all that kind of stuff. But it's nice to have something as a reference. And the sun and the moon does make a nice reference that way. Well, oftentimes, what you can do if you just hold your little finger out, that's more like a degree. It's more like 50 times as far away as it is wide if you hold it way out in front of you. And so you will easily cover the sun with your little finger, the tip of your little finger. It's not a bad 1 degree kind of reference. One of the other things I'll just mention is that Andromeda Galaxy, if you've ever seen pictures of the Andromeda Galaxy, it's enormous. If we could see the galaxy, we can see the nucleus of the galaxy, but if we could see the galaxy, it would be 4 times the size of the moon. If we could see it in the sky, when you look up where the Andromeda Galaxy is, you would see that thing that you see pictures of 4 times as big as the moon is, 4 times as big as the sun is. And it's just interesting that the only reason you don't see that is because it's just too dim. You can, with the naked eye in a dark sky, you can see the bright core nucleus of the Andromeda Galaxy, but you can't see that thing that you see all the beautiful pictures of. Okay, let's go on. Let's move on to 5. 5 is a kind of a simple cartoon, but it's a nice thing to illustrate a few concepts. It's not to scale, obviously, but it does a nice job of illustrating the concept of umbra and penumbra, the shadows of either the Earth or the Moon. In this case, we're talking about a lunar eclipse. And this is a nice diagram kind of showing these concepts. If I draw a line from the top of the sun to the top of the Earth and beyond, and a similar line from the bottom of the sun to the bottom of the Earth and beyond, the region between those two lines on the far side of the Earth is the umbra, because there's no part of the sun that's visible from inside that umbra. Now, I notice that in this diagram, it kind of suggests that there's that umbra comes to a point and then reestablishes. That's a little too bad. The umbra ends at that point. Beyond that point, the Earth is now apparently, well, I'll get to that maybe. I think you can see that if you are in the region between the top line and the top of the umbra, you're in a region where you won't be able to see the bottom of the sun, because the top of the Earth is kind of blocking your view. But you will see the sun, and it will be very bright because the sun is very bright. You don't have to see all of the sun to have things lit up. The sun is 500,000 times brighter than the moon. So
This
if
is
you're
from the
seeing,
POV of the moon, right? So you're standing
sorry,
on the. This is from the POV of someone standing on a spaceship, right? And you're
standing on a
positioning yourself.
spaceship. That's right. Now, or the moon, right? The moon is sometimes in the penumbra as well. It's shown in the umbra in this diagram, but of course it can be in the penumbra. It can't be far away in the penumbra, and it can't be nearby in the penumbra, but it can be at its distance in the penumbra. Okay, so I was just going to say that because the sun is 500,000 times as bright as the moon, if you're seeing even 1% of the sun, you have something that's 500 times as bright as the full moon. And that's why when you go to see a total solar eclipse, make damn sure that you're in the path of totality. Because if you're not in the path of totality, there's really nothing very interesting to see. If you've ever, even a 95% eclipse, a 5% remaining partial eclipse, it's daylight. It's a little dim, you're right? I feel like maybe there's some haze in the sky, but that's about it. Okay, so anyway, the idea of the penumbra there and the umbra. And the umbra is the place to be for a total eclipse. It's easy, as we'll see in a moment, for the moon to be in the umbra of the Earth because the umbra is way bigger than the moon. So the entire moon can be in the umbra of the Earth. That'll be the next slide. Just once again, I'll catch my breath here for a moment, see if anybody has any comments.
I'm not sure if you want to talk about that, but I'm always underwhelmed by lunar eclipses. Like there was one that happened a month ago, and it was pretty boring, and we couldn't see shit because it was behind the mountains, and you had to climb an entire mountain to see the
Oh
red.
man, that's really a waste of effort.
Yeah, it's stupid. I got excited and I did it, and then I'm like, what? This is like, what are we looking at here? It's dumb.
It's funny to me that I feel like in the last 5 or 10 years, eclipses in general and even lunar eclipses have taken on this new, I mean, people talk about it. I don't know if the internet must have something to do with that. I don't know why that's the case. I remember when I was maybe 12 or 13, some friends of mine and I stayed up all night at my house. They came over, we had an all-nighter, and we watched a total solar eclipse, a total lunar eclipse. And I remember just that exactly, that's what I'm saying. What the hell did I lose all that sleep for? They're just not very interesting, right? It's nice seeing the moon. You can see something different's going on. It's that reddish color, right? That's all kind of fun. But you've seen one, and yeah. The other thing about a lunar eclipse is that whenever a lunar eclipse happens, everybody gets to see it. As we'll see, it's something that everybody on the right side of the Earth can see. And so it's just not very special. We'll see the difference. Of course, with the solar eclipse, you've got to be in the right place. And that's a very small set of places that you can be. But yeah, and the other thing, of course, about a lunar eclipse is that because the Earth has an atmosphere, if you actually look at the Earth from the moon when you are in the umbra of the Earth, you see a very bright red ring around the Earth, which is sunlight being refracted and making it not very dark. It's not as dark on the moon as you might expect. Certainly not as dark as being on the dark side of the moon, because there's a lot of light getting to you, a lot of light refracting
Because of the
around
size of the planet Earth, it has way more light that could refract from its atmosphere than it's the opposite. So if you were on Earth in the path of a solar eclipse, then you will be dark.
Yeah, actually, in fact, that's not quite true, because when you're on the surface of the Earth watching a total solar eclipse, there's a lot of light getting to you from the atmosphere not very far away. So it's not dark like
It
night.
leaks from the zones that is where it's partial. Okay, okay, okay.
Right. Yeah, that's right. If you could really block all the light coming to you from the sides, it would be very dark because there's no light getting around the moon if it's a total enough solar eclipse. But there is a lot of light getting to you from the sides where where they're not seeing that solar eclipse. Anyway, we're getting a little bit ahead of ourselves. We'll get to that in a moment. But
And
this slide is just nice for showing umbra, penumbra kinds of things, and just remember that it's not at all to scale. Go ahead, Richard.
yeah, I was just going to say, I beg to differ a little bit in terms of the excitement of a lunar eclipse. I caught a supermoon, lunar eclipse, and planetary procession all in the same night over a bluff overlooking the ocean. It was amazing. I have the video of it, actually, photos and video on YouTube. I'll stick it in the link if everybody's curious.
Oh,
But
cool.
yeah, it was amazing. Trust me. Yeah.
What did
Yeah,
you said and what was the last thing you said you caught?
Planetary procession. So all the planets lined up in a row coming
Oh,
out of the ocean. Jupiter, Saturn, oh man, it was
I see.
wow.
Procession.
Trust
Yeah,
me.
right.
Oh yes, yes, it was lovely.
Yeah. Shamash, did you somebody
oh
unmuted?
no, I was just gonna ask Richard to link it somewhere in chat or
Oh
somewhere
yeah.
else so
Oh
that
yes, I will.
we can see it.
I did a really nice video of everything. Yeah, it was wow. I mean, let's put it, the moon was so bright, it was like a spotlight, I swear to God. And coming out of the eclipse, so it went very red and then very bright, like wow, because it was a super moon. I forgot which exactly. Wolf moon or one of those. But yeah, I'll put the link. This is
Good.
one of my most amazing astronomy events ever that I personally witnessed. Yeah.
Well, that's
Yeah.
good. I don't want to dump on anybody's excitement. Lunar eclipse, everybody should see a lunar eclipse. But for my taste, probably
Oh
one
no,
is
the
enough.
opposite actually. It's because people like Richard exist that
Yeah,
John and I can just sit at home and sleep on time. It's
that's right. Oh, I'll just watch that on YouTube. That's
yeah,
right.
exactly. It'll
Sunset.
be
There's no
way
need
better.
to no need to put your clothes on and get out of the basement. Just watch a sunset
Nah,
on
stay in the
YouTube.
basement. Exactly.
Yeah. Okay, well, let's move on to slide 6. This is a slide I put together. I have I should probably put, I have a one-page lunar and solar eclipse slide. I probably should put that on here too, but I haven't yet. So this is looking at the lunar eclipse a little more to scale, not quite to scale still. The distance between the Earth and the Moon is much too small. I would have to, if I wanted to do this to scale, I'd need to put 30 Earth diameters between the Earth and the Moon, and there's probably only about 10 or 15 on this slide. So this is, once again, unfortunately, not to scale, but it's getting a little closer to scale. And there are a couple things that I am representing reasonably correctly here. If you look at, first of all, just look at the umbra and penumbra that I'm showing there. The umbra of the Earth extends for about 1,000,000 miles. And that's actually easy to calculate because the half-degree size of the sun correlates directly to the umbra itself having an angle of 1/2 degree. And because the diameter of the Earth is 10,000 miles, that's astronomy speak for 8,000 miles, because the diameter of the Earth is 10,000 miles, and because the umbra is 1/2 degree, that means it has to be 100 times 10,000 miles, which makes it 1,000,000 miles. So the umbra extends out 1,000,000 miles beyond the Earth. The moon is 1/4 miles away. So when it goes through the umbra has only converged a little bit. It's still about 6,000 miles wide. And the moon, being 2,000 miles in diameter, that's astronomy speak for 2,300 or whatever it really is, 2,000 miles wide means that it fits easily, the entire moon fits easily in the umbra of the Earth if it's got the right trajectory. Lots of times lunar eclipses don't make it into the umbra. They just kind of skirt by, staying in the penumbra the whole time. And that's really not a very interesting eclipse. You really want to see an eclipse that is at least goes into the umbra, because that's when you get that reddish tint that makes which is probably the best thing about a lunar eclipse. Okay, so so we're seeing all of that. The penumbra at the distance of the moon is wider than the Earth, maybe 10,000 miles or something, maybe really 10,000 miles. And so that'll come into play here in a moment too. Everything's rotating. We're looking down, so everything's rotating counterclockwise. I'm showing this now with the sun, of course, way out to the left, way out to the left, shining light that is essentially, you wouldn't notice any difference between just saying I have light traveling directly to the right. That's traveling directly right. The Earth is revolving in its orbit around the sun at 29.7 kilometers per second. I'm trying to be a little more precise here because I need some pretty good numbers for what I'm about to do. That's how fast the Earth is moving around the sun on average. The moon revolves around the Earth. If I just for a moment go into the reference frame of the Earth, you can calculate the circumference of the moon's orbit, divide by how long it takes to go around that orbit, about 27 days, and you'll find out that it's moving at about 1 kilometer per second around the Earth. So in this picture, where I'm kind of thinking of the Earth moving around the sun, the moon is doing that too. The moon is also going around the sun at 29.7 kilometers per second. But on this side of the Earth, it's going an additional 1 kilometer per second because of its motion relative to the Earth. So I'm showing that just as 29.7 plus 1 kilometer per second. And the 1 is the important part, because if you take that 10,000 mile diameter and turn that into kilometers, you get maybe 16,000 kilometers. If you divide 16,000 kilometers, the size of that shadow, by the 1 kilometer per second at which the moon is moving through that shadow, you'll find out that it takes something like 5 hours to move through the shadow. And that's why lunar eclipses typically, from first contact with the penumbra to last contact, are on the order of 5 hours, maybe 4 to 6 to maybe 7, I don't know, but 5-ish hours is how long it takes the moon to travel through the shadow of the Earth. And I'll have a little more to say about that on the next slide, but let me just stop there for a moment, see if there's a little bit of relative velocity stuff going on, some things to appreciate. Any comments or questions? So I'll just call your attention also to the fact that on this diagram I'm showing that the Earth itself, of course, is rotating once per day. The moon takes something like a month to go all the way around the Earth. So in this 5 hours that the moon is traveling through the shadow of the Earth, 5 or 6 hours, whatever it is, during that time, the Earth rotates by a quarter of a full cycle. Essentially, it takes 24 hours to go around one full time. And that means that from the reference frame of the Earth, you're seeing this lunar eclipse moving westward, even though if you just kind of think about what the Earth looks like from its downward point of view, it's rotating west to east, and it's doing that so fast that it makes the whole eclipse, it makes the moon and the shadow of the Earth look like they are moving east to west. That's an important thing I should have emphasized as well here. When we look up at the moon, it looks like it's moving east to west, even though it is orbiting the Earth in the opposite direction from west to east, just because we're being carried around so quickly. Okay, and then that last point is what's illustrated then. If I think about what this is going to look like from Earth, looking up at the moon and the shadow, because I'm being carried from west to east, I'm going to see the moon moving to the west, and the shadow, of course, that it is entering, catching up with it. So the moon moves to the west. The shadow catches up with the moon from my point of view and then engulfs it. Then the eclipse happens, and then the shadow moves out. It looks like the shadow is moving faster, and that's just because of the fact that the moon is actually moving in the other direction, whereas the shadow basically isn't. This is a thing that is commonly brought up by people who take issue with the whole kind of heliocentric model of the solar system, because they say, wait a minute, if the moon is entering the shadow of the earth, how is it that I see the moon going to the west and then the shadow overtakes it? That is a weird thing geometrically if you think about it, and of course it's due to the fact that that we are moving. It's a perspective effect due to the fact that we're moving so fast in the other direction. Okay, any comments or questions on that before we go
So
on to the solar eclipse? Go ahead.
3/4 of the planet could see a proper lunar eclipse.
Yeah,
Do
that's
I
right.
have
At
that right?
some
Yeah.
part or another, right? Yeah, and once again, the thing about it is that everybody sees the entire same eclipse. We all see the moon going into eclipse. We all see the same thing, even if some of us are maybe carried around to the other side of the earth before it's over, or some of us aren't quite there for the beginning. The parts that we see, we all see exactly the same way. And I mean exactly the same way, because the moon is so far away. We're not even seeing we are seeing a little bit different, right? There's a little bit of parallax going on if we're at different places on the earth, but it's so far away that that's a completely negligible thing. And we see kind of exactly, we're all looking in the same direction at this thing that's happening, and we're all seeing it in exactly the same way for that reason. I shouldn't say exactly, but effectively exactly. Okay. So let's move on to slide 8, solar eclipses. Once again, this is a great diagram. I love this diagram, even though it is grotesquely not to scale. The Earth is bigger than the sun. The distances are crazy, but it's really nice for visualizing the
Oh
umbra
no, it's
penumbra
just 3D
effect.
drawn in perspective. We are behind the Earth and it's closer. That's why it looks bigger.
Okay, okay. Yeah, the problem with that, of course, is you can kind of see that shadow's being cast on the near side. So I don't know. That's
I
kind of an
tried.
Escher.
I tried. I'm sorry, I tried.
That's an Escher thing, I think, right? If you want to think that this is because the Earth is closer
Oh
to
yes,
us,
yes, exactly. I sure did this diagram exactly.
I think that's right. But it is nice for showing that the umbra, of course, of the moon gets smaller, and the part of the Earth that's in the umbra is smaller than the moon. Indeed, as we'll see on the next slide, as I think you all know, that's one of the remarkable things, is that it's a very small part of the Earth that's in the umbra, whereas a much larger part is in the penumbra. Seeing a partial solar eclipse during a total solar eclipse, if you're not in the path of totality, you see a partial solar eclipse. And there's a very large range of very large region over which you can see that partial solar eclipse. Okay, I think that's enough said there, but that is a really nice one for just kind of showing that umbra penumbra thing, even if it's grotesquely out of scale. Let's move on to the next. Oh, and by the way, that slide comes from a really nice discussion of the eclipses. If you can of course find all sorts of stuff on the internet about eclipses, but this is a really nice place that I just found when I searched for some diagrams. I found this diagram and I looked at it a little bit. It's a nice page talking about eclipses, so I put the link there as well. And the next page is another slide from the same thing, illustrating the effect of the fact that the umbra of the moon ends just about right at the Earth. The umbra comes to its point right about at the Earth. And sometimes when the moon is a little further from the Earth, or maybe the sun is a little closer to the Earth, so that the moon is a little smaller in apparent size than it normally is, or the sun is a little larger in apparent size than it normally is, both of them are remarkably close to half a degree. They're both on average a little more than a half a degree. The moon varies in size more because its orbit is more elliptical around the Earth than is the Earth's orbit around the sun. But that just means that sometimes the tip of the umbra ends before it gets to the Earth. And sometimes it ends after it gets to the Earth. And sometimes the Earth, the tip of the umbra never even touches the Earth. Sometimes part of the Earth passes through the umbra without the tip even touching it, like shown in the bottom slide there for the partial eclipse. In cases like that, nobody on Earth gets to see either an annular or a total eclipse. They'll just see a partial eclipse. But the difference between the total eclipse and the annular eclipse is simply whether the tip of the umbra makes it to the Earth. If it does, then there will be places on Earth where you can see a total solar eclipse. And if it doesn't, there will be a small region of places on the Earth where you can see the sun ringing the moon. You have to be right behind the tip of the umbra during an annular eclipse to see an annular eclipse. So it's still an interesting place to be, but it's far less interesting. There's no reason to go to the path of annularity. The path of annularity is a very small path. Very few, I would say probably far fewer people have seen an annular eclipse than have seen a total eclipse, because people travel to see a total eclipse. And you have to travel to see an annular eclipse, but you don't, because they're not very interesting. It's still broad daylight in the path of an annular eclipse, because if you're seeing even 1% of the sun, that's 500 times the brightness of a full moon. Okay, any comments, questions on that? Okay. So let's go on to a couple slides that I made, like for the lunar eclipse. This is the solar side of my slide, which I will share at the end. I should have put that in here. The solar eclipse now. So similarly, I'm showing now the moon and its umbra and penumbra. I'm once again, I have the sun way off to the left, way off to the left. We have the moon now casting a shadow, very much like the Earth did before, with its umbra coming to an end about 100 moon radii away from the moon. Amazingly enough, 100 moon radii gets you right to the Earth, gets you just to the Earth. The distance between the moon and the Earth is about 100 lunar radii. That's why it is a half a degree in apparent size from the Earth. That's why the tip of the moon's umbra just makes it to the Earth, or maybe just doesn't make it to the Earth, as we just talked about. And so there it is. And we're looking at the situation at the very beginning of a solar eclipse, because at this point, there's the Earth once again moving 29.7 kilometers per second. But now, because the moon is on the other side of the Earth, its orbital velocity is opposite that 29.7, meaning that it's moving relative to the sun at 29.7 kilometers per second minus 1 kilometer per second. Once again, then there's this same 1 km/s relative velocity, but now it's a motion in the opposite direction. The motion of the shadow across the Earth is as it's shown there. It's in the kind of downward direction in this diagram because the moon is moving slower than the Earth is, or if you want, is moving in the downward direction relative to the Earth. So there's the basic geometry. The shadow's moving at 1 km/s in the direction shown. Meanwhile, the side of the Earth that's facing the moon is also moving downward. I have indicated it by showing it as 15 degrees per hour. 15 degrees times 24 is 360. So that's about right. It's about right. It's close enough for our purposes. The Earth is rotating at 15 degrees per hour. Notice that's west to east. If you kind of have to kind of think about looking at the Earth, thinking about the continents on it, thinking about directions, and you'll see that looking down on it there, that's a west to east rotation of the Earth. And so this sets up the question that I indicated at the beginning. What direction is that shadow going to move on the surface of the Earth, given the fact that the surface of the Earth is moving in that downward direction and the shadow is moving in that downward direction? And maybe we'll just stop here for a moment. If anybody has a comment on that, we're going to work that out here pretty quickly. But that is the central question. It's not obvious because of the fact that the Earth is rotating that way and the shadow is moving that way. It's not clear whether the path on the Earth is going to move west to east or east to west. And I'm just going to stop for a second because this is
right
kind
to
of an important
suspect
point.
that your latitude would play a role here?
Okay. Yeah, explain. I understand what you're saying, but explain that a little more.
The thing is, according to your latitude on the planet, the angular speed of rotation of the planet would change. And this is exactly what we're talking about. So these are the two factors. The actual speed of the moon is the same, but your perception of it, because you're standing on the planet, would change. And so because you are probably next to the poles, then your rotation will be very, very slow. And so the bigger factor would be the speed of the moon itself. Whereas if you are on the equator, then the speed of rotation of the planet would play a much bigger role.
Good. Well said. Yeah, exactly. There's lots of other things to talk about here, so I'm just going to stop for a moment, see if Benjamin or Richard wants to say anything about that.
Benjamin doesn't play with these things. Benjamin
No,
plays
he doesn't. He's not. He's just thinking about
doesn't-
thinking about what he's going to say when we get to the good stuff.
Did have actually some comments, but I'll wait till the end because just on the perception of the size and motion of the moon for humans, given that we're using our eyes and our brains, and there's some interpretation going on there that doesn't necessarily reflect reality, especially when we try to capture with our cameras, and it's like, well, why doesn't it look the same on the camera as what I witnessed with my eyes, etc. So to talk a little bit of that at the end.
Right. It is. I mean, it's worth for this kind of thing. It's worth thinking about if you ever see a solar eclipse. If you look at it, it's worth kind of paying attention to what direction that shadow kind of crosses the shadow of the. It's not the shadow of the moon. It's worth kind of paying attention to how the blockage that the moon shows on the sun is moving relative to you. I did this recently. I took pictures of a partial solar eclipse that I knew had kind of crossed from northwest to southeast across southern Utah. Kind of the closest point of approach to Los Angeles was southern Utah, and I knew how far away that was, and I knew how much blockage. That was the total eclipse there. I had a partial eclipse, and because I could estimate about how much partial eclipse I was seeing, I could determine very easily from knowing how far it was to the total and how much partial I saw, the distance to the moon. This is what the Greeks did 2,500 years ago. They knew how far it was to the moon. They knew it was something like 250,000 miles. They didn't have it accurately, but it's easy to measure the distance from the moon just from observing eclipses from a couple of nearby places and seeing how the shadow changes from parallax. So the Greeks were well aware that it was on the order of 250,000 miles to the moon, and they knew that the sun was much further away than that, but they didn't have good enough measurements to be able to make a very accurate measurement. They had good enough measurements to know that it was much further away, but they didn't really know how much further away. So, and that's an important point when it comes to Eratosthenes' experiment. A little brief aside. Eratosthenes assumed that the light from the sun at all places on Earth was in the same direction, which it is, because of the fact that the sun is enormously far away from the Earth. And the Greeks knew that for sure. Okay, so let me just say one more thing about this then. Shamash, you made the most important point about this diagram, and that is that the linear speed of a person on Earth will be different at different latitudes. So maybe it's worth just taking the maximum linear speed, which happens at the equator, and comparing that to the 1 kilometer per second motion. But even rather than, I'll do that in a moment, but I'll just point out that if you take 1 kilometer per second and you take the diameter of the Earth, which is about close to 13, is that right? No. It's about 12,500 kilometers. 12,500 kilometers is the diameter of the Earth. If you divide that by 1 kilometer per second, you get 12,500 seconds. 12,500 seconds. How many hours is that?
Around 4 hours?
That's around 4 hours, right? 3,600 seconds per hour. So 4 hours, that means that the shadow of the Earth, a shadow of the moon, will cross the entire diameter of the Earth in about 4 hours, 4-ish. 4, 5, 3, whatever you want to say, 4-ish hours. Oh, no surprise, that's the same as it was for the lunar eclipse, right? The lunar eclipse lasts a little longer because the full shadow is a little bigger. But in this case, the shadow crosses, and if you want to take the full shadow, that's going to make it a little longer too, because the full shadow of the moon is a few thousand kilometers more. So maybe that makes it 5 hours. But the shadow of the moon will cross the entire diameter of the Earth in 4 or 5 hours. Meanwhile, how long does it take a person who starts at that top of the Earth to make it to the other side, the bottom of the Earth? I should say the bottom, but of course we're looking down on the Earth.
Half a turn, right? So
it's going to take half a turn, right? Yeah. So that's 12 hours. And that should be enough right there to demonstrate that it doesn't matter where you are on Earth. You're not turning fast enough to keep up with the shadow. The shadow's making it all the way across the diameter in 4 or 5 hours. You can't do that in less than 12 hours. So you're going to see the shadow move to the east because you can't move to the east yourself. No, even at the equator, you can't. And if you work out the speed of the Earth at the equator, you'll see that it's about 400. Is that right? Let me just, what is it, 1,000? I didn't do this. I should have done this. It's about 1,000 miles per hour. 1,000 miles per hour is about 1,600 kilometers per hour. So if I divide that by 3,600, I get, about 0.4. So even at the equator, your velocity is about 0.4 kilometers per second, which isn't enough to keep up with the motion of the shadow. Okay. So on the next slide, I show what that looks like, and I'm showing kind of specifically what we get. There's the umbra surrounded by a penumbra. you see kind of this fuzzy, largish shadow with a tiny little, completely dark spot at the center moving across the face of the Earth. It begins when that shadow first contacts the Earth on that side and then moves across the diameter of the Earth, the diameter-ish of the Earth, in about 4-ish hours. Meanwhile, the Earth itself rotates through about 4 times 15 degrees, 60 degrees. So I'm kind of trying to show you there the Americas moving about 60 degrees across the face of the Earth while the shadow moves all the way across the Earth. And you can see why we would expect then the shadow relative to the Earth to move from west to east. Okay, so any comments on that? So we're basically done here, just a couple of little niceties to talk about, and then we'll open up. We can talk about quantum entanglement. I know Benjamin is itching. Okay, so let's go on. Slide 12, actually, I don't know if you've seen this before, but it's very cool. These days we have weather satellites, especially the GOES satellites. If you go to the GOES website, GOES, the GOES imagery website, you can see all sorts of great real-time pictures of the Earth. You can get a picture of the Earth, see what the weather looks like right where you are right now. They do animated GIFs of the last 24, 48, 72 hours. You can watch how the weather's developing. It's a great website, so I should have put the link here, but this is a video taken from the GOES weather satellite. Actually, is it? I think so. I think it is. The Atlantic version. There's a couple of them, one out over the Pacific and one that covers the Atlantic. They're both in equatorial geosynchronous orbit. So this video, I should caution you, this is, in this picture, you won't see the continents moving. And the reason you won't see the continents moving is because the satellite is moving with the continents. So the only thing you're going to see is the shadow itself moving. And if you play that video, you can watch the daylight kind of overtake the region. You can see the eclipse going up. This is the April 2024 eclipse coming up through Mexico, across southern United States, and on off into the North Atlantic. And you can see, all you're seeing there is the penumbra of the moon. That's the penumbra of the moon's shadow. At the very center of that, there is a completely dark spot, but the exposure isn't such to even be able to notice that. You just notice that it's darker around the umbra in that penumbral part. Anyway, I think that's a pretty cool video. There are videos, I think, we have satellites also at the position called L1. That's a position that's 1,000,000 miles away from the Earth on the sunward side. And if you watch videos of eclipses from that satellite, you'll see the Earth slowly rotating while, I should have put a link to one of those too, while the shadow moves across the Earth. Of course, once again, west to east. But in a satellite at L1, this is a satellite from which we always see the Earth in day. We're always seeing the day side of the Earth, and therefore the Earth itself is rotating west to east, as seen from those satellites.
It's a very cool video, by the way.
It is very cool, I think, and there's just lots of videos like this now because the satellites are always doing this. I just wanted to end with this. There's a really interesting thing called the Saros cycle, which eclipses come in kind of patterns that repeat. The Saros cycles are these patterns of repeating eclipses. This isn't long enough to show you anything that looks like the Saros cycle, but it just shows you the path of totality of lots of eclipses. And if you look carefully at it, first of all, you'll notice that eclipses in the Arctic region are weird. And if you think about why that, the reason for that is because the shadow of the sun now is first of all, the moon and the sun are right on the horizon. When you see an eclipse in the Arctic regions, it's always on the horizon because the sun is never where but on the horizon in the Arctic regions. And that means that the shadow is coming in at a glancing incidence to the Earth. Sometimes the shadow can even hit the Earth on the other side of the pole if the pole is facing the moon at that time. You can see an eclipse from the other side of the Earth because you're still seeing the sun. You're in 24-hour daylight, and that means that eclipses in the Arctic regions are weird, and you can think about that more. The geometry is tough to appreciate, but you can think about that if you like. One thing you can, I'm going to just leave it as kind of a challenge for you to understand, is that if you look at all those eclipses, you'll notice that all of those paths in the winter are smiles. They all curve upward. They're always smiles. In the summer, they're always frowns. They always curve
winter is
downward.
blue, right? And summer is red.
Sorry?
The color coding, so winter is blue, summer is red, right?
I don't think, no, it isn't. I actually don't know why the coding is what it is. I don't know if those are annual. Maybe it's annular versus, I'm guessing it might be annular versus total. Sorry, I really should have paid attention to that. I didn't even think about it. But it's not coding those. It's not coding winter versus summer. But if you look closely, and you might have to look on a computer at this diagram, you'll see that they're all labeled with the dates. All of the winter, December, January to February maybe, eclipses are smiles. All of the summer eclipses, June, July, maybe May, June, July, that region are frowns. They curve downward. Fall eclipses always kind of curve as well, but they run from the north to the south while they're going east. Spring eclipses always run from the south to the north while they're heading generally east, and of course are curvy as well. That's not too hard to understand. You can probably guess immediately what it must have to do with, but it's worth thinking about in terms of a diagram, kind of like those that I've shown you, and thinking about tilts of things and understanding why that makes total sense. So that's, and I'll just kind of leave that. We can talk about that if you want, but I love seeing things like this and looking and then thinking a little bit more three-dimensionally than we often do, to appreciate that there's a pattern there, which once again is a result of this very simple model. The model's pretty simple: a moon orbiting an Earth while it orbits the sun, in planes that are tilted relative to each other, so while spinning around axes that are tilted. There's a lot of stuff going on, but you can kind of put that all together and see, at least to first order, why things work the way they do. And that's pretty much all I want to say. We can talk more about this diagram if you want, or we can just move off into anything else. Oh, there's Addy. Let me bring Addy on stage, if he's not already. Hi, Addy. Welcome to the stage. I don't know if you've been here before, but welcome to make a comment or whatever you like.
John, very quickly, if you look at that last diagram, there are certain paths that are thicker than others. Does this have to do with the distance from the Earth to the Moon? So at some point, the Moon was closer, and that makes the line thicker?
Yeah, so I think that the thickness of the lines is at least intended, if it doesn't specifically show the path, the width of the path of totality, which I don't think it does. I think it's at least intended to show the relative widths. So the wider ones would be the result of a moon that is relatively close to us, and or a sun that is relatively far away from us, whereas the thinner ones would presumably be, the opposite. And I don't even know if there are well, I did say annular, didn't I? So I didn't spend enough time looking at the source, and I didn't write down the source. I'm gonna have to find this diagram again and understand it a little bit better. Anyway, were you going to make a comment on that?
This is very interesting. No, I'm just asking to see.
Yeah.
And another thing that caught my eye, for example, is that, well, if those paths are a cycle, as you say, and they repeat, does this mean that there are places on the planet that will never see a total eclipse?
I doubt that that's the case. But it is the case that the Greeks, I think, at least very, very early on, this cycle was known, which is surprising to me, because it's not and I don't remember how long the Saros cycles are. I think they're on the order of a century. But it's surprising to me that they would have had enough data, given the fact, especially, that a total solar eclipse in a region like Greece or even the Middle East just doesn't happen that often, to be able to compile the kind of data you'd think you'd have to really even notice the cycles. But those cycles were noticed early on, and they were used to predict pretty accurately when other eclipses would happen, even though they couldn't be used to predict the precise path of totality. They couldn't tell you where you would have to be to see the path, but they could tell you kind of when it would occur, and approximately where it would occur. We've got Astro Boy on stage 2 now. Any of the new people on stage, we're in open discussion here, so fundamentally, basically popcorn. If you'd like to say something, unmute and do so. Oh, scared him away. But the fun thing with eclipses up there in the Arctic regions, they're running. I want to say they're running west to east, just like usual. But if a west to east path passes on the other side of a pole, that's an east to west path, right? A path like on this Mercator projection, a path that runs from one side to the other, but that occurs on the other side of the pole, is going to be a path that's essentially running the other direction, running east to west. So there are those kind of weird exceptions. And the paths up there are very weird because of the way as I mentioned, the slanting, the fact that the eclipse is being seen on the horizon leads to all sorts of odd things. Another thing that it leads to is the fact that the velocities of these paths of totality vary enormously over the path. When the eclipse first hits the Earth and when it leaves the Earth, it's passing over a region of the Earth that's kind of parallel to the path, right? It's coming onto the edge of the Earth. So it moves really quickly across the first part of the Earth, because that part of the Earth isn't moving. And then the same thing kind of isn't moving in the direction of the path. It's moving toward the sun originally, and at the end it's moving away from the sun, while the path is still moving perpendicularly. So the early and final phases are very rapidly moving. If you want to see your longest totality, you'd like to be at the part of the path where the sun is directly overhead, because that means you're going to be moving very quickly in the same direction as the shadow, trying to keep up with it. And to that end, I should also mention that, people try to get in planes and move and stay in the eclipse. You can't do that, because, at least not with a passenger plane. Passenger planes, subsonic planes, can't move fast enough to keep up with the shadow. That's how fast it's moving. I see Adi seems to be aware of that as well. Anyway, complete popcorn. Now we can talk about this. We can talk about anything else, Benjamin. That's
I
my
would like to ask
permission.
about any new experiment in quantum mechanics that would eclipse any result that happened before.
Nice segue, Shamash.
Yeah. Learning from the best. Learning from the best.
Yeah. Yeah, and if
One
anybody else would
comment,
like to come up on stage and join us, you're welcome to do so. Raise your hand. We'll bring you up.
one comment I did want to make, alluded to earlier, was the relative size of the moon when observed by humans, and kind of the mystery to that. I'll stick
The perceptual thing.
yeah, because I find that always intrigues my astronomy friends and the kids we're teaching. That well, why can't I photo the moon? When I see it and I photo it, doesn't look the same. But da 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 da. And there seems to be some mystery behind that. Continuing, I'll stick a link to a NASA a paper on it, article on it. But yeah, it is intriguing. Did you have any comments on that or any
Yeah, I definitely do.
enthusiasm?
Because I think what you were just saying there, you're exactly right. I think it is a common thing that when you see, especially a full moon rising for some reason more than setting, I don't know why, setting too, but especially a rising full moon can look just enormous. All right, it's perceptually enormous, and there are lots of, I think, good explanations for that, but but they don't. But they're they're competitive. I mean, you can't. It could be this. It could be that. Maybe all those things are in play, but people don't entirely understand. What's the most important thing, because it's perception. It's a perceptual effect. We know it's not a real effect because you can take pictures of the moon on the horizon, count pixels, and what you'll find is it's actually smaller on the horizon than it is when it's overhead. It's physically
Oh,
smaller in the
really?
vertical direction due to atmospheric refraction. It's not smaller in a way that you'd really notice, but it is. You can measure that it is vertically compressed if you take a picture and count pixels.
So it's only happening in our heads.
It's completely in our heads, that's for sure, because
Okay,
you can
okay. I
measure
thought
it,
there's some
and it
weird reason
isn't.
because of refraction, because of whatever. I'm guessing now that it's because it would be closer to the mountains behind it that our brains get tricked, if that is the case.
That's one of the explanations, is that when it's on the horizon, you're comparing it to things you know the size of, and you kind of know that the moon is much further away than them, and so it's got to be enormous. It's a weird thing because you don't know, because you don't kind of perceptually know just how far away it is, right? And so it's
Or how
weird.
big it is. It's a fucking planet, right? It's
Right,
huge.
right. Another explanation, maybe Richard talks about it, but another thing has to do with just our perception of the sky itself. We perceive the sky kind of as a dome-like structure, not really a constant distance. And so when something is on the horizon, we think of it as apparently being much further away, and then perceptually make it bigger. Is that one of Richard? I don't know if you want to say a few more words.
Sure. Well, that's why it's kind of points to the importance of accurate measurement and not going with intuition, because leading
Right,
into flat Earth nonsense, right? This idea of, oh well, if you see it with your eyes, you gotta. It's like, you can't beat measurement, and often your mind can fool you. And if you're not aware of that, and I like this issue with the moon because it is a constant reminder, very large scale, of why we should not just go with our quote unquote eyes and intuition. That
right,
scientific principle, that measurement is important because we have to clearly define what we're dealing with and draw our inferences from the accurate measurement and not from our, opinions and perceptions, because that can very often be wrong. And thank you, Moon, for that, because I think that's
right,
a great way to kind of highlight that point, which I like to do for the kids I'm working with. That it's important to have that science in your mind, to be aware that you can't just go with observation
right.
to measure.
Yeah. No, I think it is. It's a really good illustration of that fact. I have, to that end, one of the things that I'm doing this year, I think I've talked about it here before, I'm taking pictures of the sun every Sunday. And so I'm calling it my Sundays project.
Is
And
it like a
I'm
ritual for the sun god or for?
oh, in fact, let me get this thing here while I'm thinking about it. Anyway, I'm taking pictures every Sunday, and then I take the picture count. I count the pixels. I fit a circle, fit an ellipse actually, just by eye. I just fit an ellipse to the form of the sun. And I'm taking these pictures from all over the place. Some of them, sometimes I've been in Alaska. Pretty soon I'll be in Italy when I'm taking them. And then later on I'll be in Panama and then Hawaii. It doesn't matter where I am because the sun is the same size viewed from anywhere on Earth because of the fact that it's so far away. And the only thing that makes it change its size at all is the fact that over the course of a year, it changes its distance from us by about 2 or 3%. So that in January, when it is closest to us in the winter, in northern hemisphere winter, the sun is closer to us than it is in the summer. It's the biggest it ever gets. It's 0.542 degrees in angular diameter in early January, which is perihelion. And then in early July, when it's farthest from us at aphelion, it's 0.524 degrees in angular diameter. So I've been doing this Sunday project. I'm going to put this link in the chat. Sun.
So the difference is about 0.002 degrees in the sky.
So it's not degrees, right? It goes from 0.542 degrees to 0.524 degrees. That's a really nice. It's an easy thing to remember because all you need to remember is the 4 and the 2. The 0.5 comes from being a half a degree, and then you just tack on 4.2 and 2.4. That's the range of angular sizes. If you look at the spreadsheet, the Google sheet that I just put in the chat, you'll see a graph in it of the results so far compared with the predictions of the heliocentric model. And I'm pretty proud of it. The data, I'm typically getting, my sun sizes are typically like 2200, 2300 pixels. And I'm getting within 1 or 2 pixels of what it should be. Which is just basically my ability, maybe 3 pixels, which is just my ability to kind of determine where I think the light of the sun turns into the dark of space.
I would like to submit this Google Sheet to our data expert, Benjamin, here, and he can examine his data and see whether you are counterfeiting something or...
Yeah, well, he certainly can't accuse me of not sharing my data.
Yeah, exactly. That's pretty good of you, John. This is proper science, as you see. You're learning.
It's Claire's law. Yeah. So once again, all's fair. We want to talk about science. It'd be nice to talk about eclipse-related stuff, but we can talk about whatever anybody wants to for another half hour, maybe, or something. Unless we run out entirely. Go ahead, Eddie.
Yeah, I just wanted to ask, what is the relationship between the distance between the Earth and the Sun and the distance between the Earth and the Moon when it comes to the eclipse? And
when it comes to what?
When it comes to the solar eclipses, and in what conditions are the annular eclipses seen? Is it like the Sun has to be close and the Moon has to be far?
Okay, yeah, right. So the basic thing, the kind of first order thing to understand is that the moon is essentially in a circular orbit around the Earth, and the Earth is in essentially a circular orbit around the sun. It's the fact that it's not exactly a circular orbit that leads to the annular versus total solar eclipses. And then it's that in conjunction with the remarkable accident that those distances make both of them approximately the same apparent size. That is really, that's the central coincidence. And of course, this is, a lot of people would say, oh, you think that's a coincidence? The central coincidence is that they appear to be about the same size. And that is a result of the remarkable fact that the sun is approximately 400 times further away and approximately 400 times bigger than the moon. So the moon is quarter. I always think that the best thing is to carry around approximate numbers, and then you can kind of remember which way it goes. So I always remember the moon is 250,000 miles away. Now I know that's a little too big. It's more like 240,000 miles, but 250,000 will work. If you remember 250,000, that's going to put you in good shape. The sun is approximately 100 million miles away. That's 400 times further away. Really, it's 93 million miles away, but 100 million miles is close enough, and it allows you to see
That's
right
why we
away
use
that
fucking
it's.
metric. That's why we use
Yeah,
fucking
right. No, that's actually a good reason to use the English system, because 100 million and 250,000 are way better than 1.6 million and or 160 million and what is it,
No, it's not
390,000.
160. No, wait. It's between 153 and 147, so it averages at 150,000, 150 million. It's
Oh,
a very
100. Oh, you're right. Actually, the metric distance to the sun is pretty good, but you have to have the one that you can't. The problem with numbers that begin with one is if you want to make them accurate, you're going to need the second number too, right? You can't just say, oh, it's about 100 million. Or, oh, it's about 200 million. You have to say it's 150 million. And that's boring. I don't want to have to use
what a great
two
reason to
two
mess up the
numbers.
planet with weird units. That I'm very convinced.
Okay, all of that is to say that when we do it right, we're gonna not just we're not just gonna go to 93 million. We're gonna go to what it really is. Go ahead, Benjamin.
John, I want to apologize for not being here earlier. I know there was some failed
You were here
attempts to
pretty early,
troll
Benjamin.
me and other
Oh,
things.
I
It
see.
was
But you what you mean to say is you just hung up on the presentation, and now you're realizing that you're late to the after party.
and um, and I know that the conversation drifts into preferences when I'm not around. So I apologize for allowing
Well,
it
it's
to
no
carry
need to
drift.
apologize. Just realize that if your ears were burning, that's what was going on.
Just a little bit. I mean, I was in another conversation about in real life about uh, T-Rex.
About T-Rex.
T-Rex, yeah, T-Rex. We're talking about car. I don't know if you're familiar with car T-Rex, but um, that's we were having a scientific
So I
discussion
had a
in
conversation
real life.
about T-Rex the other day when I was talking about the
You
fact
know
that,
that T-Rex won the Nobel Prize this year, right?
is that right?
Yeah,
I guess I
T-Rex won the
No,
Nobel Prize
that's
in
not
history.
right.
okay, I feel like I'm missing the joke
Can
here.
we can I just insert a point of order? Adi was asking a question and we kind of digressed. I just want to make sure that he heard his answer before we start talking bullshit.
Yes, I kind of got my answer. The main thing is it's the coincidence that the moon is nearly the same size as the sun. That's it.
Yeah, that's right. And you can. I think the thing is that you can believe that or not, right? It's if somebody says, "Oh, you think that's a coincidence?" Yeah, I do think it's a coincidence, but I can't prove to you that it's a coincidence, right? Maybe it has some deeper meaning. I could never prove that it doesn't. But I do know, I mean, we do know that the moon is moving away from the Earth. So we know that, millions of years, probably more like tens or hundreds of
Yeah.
millions of years, it won't be the case.
So we are lucky to be living at a time when we can observe eclipses.
Exactly. Exactly. Yeah. No, thanks for your question. I'm sorry we didn't kind of finish up on that. If you have more to say, you're welcome to do it.
No,
Go ahead,
I
I'm
Ben.
think
good
that's
with
Oh,
talking about
let, wait a
T-Rexes.
minute.
I
Let's
like
let me just
T-Rexes.
hear from Addy for a second, Benjamin. Go ahead, Addy.
I'm good with talking about T-Rexes. I like
Yeah.
T-Rexes.
Well, let me. It's good. Well, let me say a couple things about T Rexes. I was talking with somebody the other day. Well, it turns out once again, this always comes back to flat Earth. I spend way too much time with flat Earthers, but they inspire me to do lots of fun things, and so I kind of appreciate it. And one of the things that's interesting about flat Earthers is because many of them are, most of them, I guess I would say, are driven to it thinking that somehow it's a Christian thing, even or that's a religious thing, right? It's a biblical thing, even though the Christian church never embraced the flat Earth. It was known that the Earth wasn't flat before there even was a Christian church. A lot of them think that it is that kind of a thing. Some of the best flat earth debunkers are young earth creationists, people who believe that dinosaurs rode on a boat with humans a couple thousand years before Aristotle and all those people. And I find it really, they are some of the best flat earth debunkers precisely because people who believe dinosaurs rode on a boat with humans, are embarrassed by flat earthers for their religion. I find that I'm sorry, and
This can't get
I
any
don't
better.
mean to poke fun at Christianity, but I find that deliciously ironic.
I was going to say I thought the question was a really good one. Was it Adi that asked that why is the moon roughly the size of the sun? I mean, visually, and
Yeah.
so there is like one weird explanation potential, which is the anthropic principle,
Mm-hmm.
which is that you need a sun of an approximate size in order to gin up waves and tides and currents in order to create the kind of opportunities for life that would lead to sentience.
Well,
I can't
I
pin
think
that
it's
precisely, but I think in general terms, you'd be hard pressed to do this if you didn't have a sun that was big. And if it wasn't the size of the sun visually, it might not be create enough waves. And if it was bigger than the sun might be too small, and you might not have enough energy and heat, and you might freeze, for example, and all kinds of things. So you could do kind of an analysis to see what the boundaries are along these lines if you agreed at all with those.
Yeah, well, there's lots of things I think you could say about the need for the sun to be something like what it is, right? We look for Goldilocks zones when we're looking for
Yeah,
life in
yeah.
other solar systems. But I think it's harder to make the case that you need a moon to be the same size as the sun. It's probably pretty easy to make the case that you need something to generate some tides, right? I mean, if you didn't have tides, it would be a very different planet. A lot of things would be very different. And that might even be a problem. I don't know exactly how, but you could imagine that being a problem. But you do generate tides. Even if we only had the sun, you'd still have tides. And you don't, and there's no reason a moon has to be the size of the sun to do the same kind of a thing. I don't think. I mean, I'm saying that, but I'm open to
Uh,
somebody kind of showing why you do. I don't think you could, but
the speed of rotation of the planet has nothing to do with the size of the planet or its distance.
yeah,
It has to do with its initial conditions and how it was formed. And so that would be a much bigger factor, seeing the tides and all that, than having a small moon orbiting you around the place.
right. I do think anthropic principle. I mean, the basic idea is, why, how do you explain the fact that everything's so perfect for us? And of course, the simple answer to that is, well, we wouldn't be here if it wasn't, right? We developed to take it. Why is it? What a coincidence that our eyes are sensitive to precisely the part of the electromagnetic spectrum that the sun puts out most of. It's pretty obvious why that
Uh,
would be the case,
Yeah,
right?
that's pretty obvious, man.
Yeah,
And
that's fair.
also the part of the spectrum that filters through the atmosphere. And
Yeah,
that's basically why plants are green.
yeah, right. Hey Ben,
S-
Well,
we've got Ben. We're joined by
what
Ben Tristram.
Oh,
Good to see
fun have
you,
oh,
I
Ben.
Ben
been
is
missing?
here.
What fun have I been
Just in
missing?
time.
Hold on a
Just in
second. Yeah,
time.
you're right. Yeah, let's hear from Ben.
No, just what fun have I been missing? Where are we jumping in?
You,
I was
you've
hearing
missed
you
the
talking about
boring.
Eclipse.
You've missed the boring stuff, and right now we're about to move to quantum mechanics.
no, we're not. No, well, not while I'm here.
And
But the bit about constraints on exoplanets is pretty interesting. I quiz them down at the Institute of Astronomy about that regularly. There was a breakthrough a few years ago that they realised that the Goldilocks zone could be a lot more flexible than they think. You could have pretty cold stars, pretty small
right.
cold stars, and you could have planets pretty close to them, and that might work. And I think there's a lot of people trying to put a lot of constraints on this from a lot of different directions because they're finding exoplanet candidates at the rate of, I think it's 200 a week or, and that a lot fast, put it that way with the modern telescopes. So they need to filter them down to make
Well,
sense of it.
and it's interesting too because of course, I mean, part of the push for that end of the spectrum rather than the end of the spectrum where you have planets really far from really bright stars, right, which you could also imagine as a part of the Goldilocks zone, is because we don't discover those planets. If there are Earth-like planets really far from really bright stars, we just don't see them because they have incredibly long periods and incredible amounts of space that's going to keep them from perturbing the motion of their star, going in front of it. We're not going to discover planets like that. The planets that we discover are inordinately biased towards close, short period around small, and if they're habitable, around small, unbright stars. So that's what you're going to care about.
We're
John,
making
to even to extend on that, let's not forget moons that are, experiencing gravitational flexing and create,
Yeah.
Goldilocks type environments within those moons and, release even chemical energy from deep within to, potentially feed any form of life that could depend on that. So I want to throw
Yeah.
that in there as well.
To add to this, the number of estimated ice moons in the galaxy is far more than terrestrial planets such as Earth or Venus or Mars.
More than rocky planets, you're saying?
Yeah. The
Yeah.
ice moons are far
It,
more
it
than.
makes sense, doesn't it? I mean, I've always kind of thought that too, because if you just take the primordial matter that a solar system is built from, it's primarily hydrogen, helium, gases, low things. And so you'd expect that where does rock come from? It's not even clear how you get rock. I don't know what planetary scientists say about that, how rocky
Yeah.
planets form.
How you get rocks in the interiors of planets. Like once ice accumulates to a sufficiently vast volume to become like spherical, then it starts differentiating and the heavier elements start settling inwards.
Oh,
That's how you get a metallic core or maybe some asteroid like Psyche.
so it sounds like, Addie, what do you work in this field? It sounds like you might.
Oh no.
No, but that's a good point. I mean, the
There's
idea
different
that
classes of rocks, though, John. Of course, igneous, sedimentary, metamorphic,
well,
all
no,
that type of
but
stuff.
what I mean, I don't mean that so much as I think it's a good point that you can imagine all planets being gaseous in the original phase, but nearby planets would have the gases evaporate away more quickly, leaving the materials from which rocks can form behind. And I don't know if that's what planetary scientists think or not. It's what Adi said. Just kind of, I haven't really looked into that, and what Adi said sounds to me like it makes sense.
Yeah, so you're right. The gases do get blown away, which is why you have a lot of dust close to the stars. and that is why you have the rocky planets forming closer to the host stars, and you have typically one gas giant that dominates the outer solar system. It is very rare to find a
Can
star system
can
with
can I
two gas
question?
giants.
Can I question though this claim that the gases get blown away? Because I don't think they can go very far unless they're stolen by some other mass. Am I
They just
wrong in my
evaporate,
thinking?
Yeah, it's
and
not
they're
a
blasted away.
right. Yeah, and it's
Well,
not even
evaporation doesn't
evaporate
make
at
them go
some
away.
level, right? I
Sublimate,
So
mean, you
sublimate.
I think I know what the disconnect here with Ben is, though. Ben, I think I think Benjamin's alluding to escape velocity, and that the gases don't seem like they'd be able to get very far because they don't have enough velocity. But the when you calculate the speed of gases at reasonable temperatures, especially light gases, they are beyond escape velocity a lot of the time. We
well, and
we
the
lose helium on the Earth and hydrogen particularly just because some of them make it out. It's just that they have a bit of an obstacle course to go through
Yes.
of the atmosphere on the Earth. But once the gases are being evaporated from the upper atmosphere, and there's nothing for them to go through, it's all about mean free paths and probabilities. But they very much the gas molecules have enough velocity to fully escape and be captured by another planet, which is quite surprising but true.
And the other thing I think to kind of appreciate is that in the early solar system, you're going to swirling thing. You're going to have a big central gas blob, a big central cold gas blob. But little eddies and things can form other little gas blobs orbiting that gas blob. And then that central gas blob starts burning nuclear fuel and gets hot. And that hot gas blob in the center is going to have an effect on the nearby gas blobs just because it's now hot. I don't, and once again, I'm just saying all this. I don't know if that it may be reason that that's not what happens, but certainly in a proto star environment before the star really turns on, you've got gas just doing what it does because of gravity, with no thermal component to think about.
Hey, wait. There is something known as the ice line apart from the gas line. This is the line beyond which ice exists. So, which is why you don't have much ice in, say, the asteroid belt. So that is like beyond Jupiter also. So there you have dense planetary bodies such as the ice giants, Neptune and Uranus, which wouldn't form even a little bit closer where the gas giants form, such as Saturn and Jupiter. And then even more closer, you only have rock. Because
Yeah,
the
thank you.
gas...
So we've been joined by I can't bear not saying this. We've been joined by Wooby Booby, or is it Wubby Bubby?
Yeah, it's Wubby Bubby, sir.
Wubby Bubby. That's nice. I like that. I bet that's not your real name, but go ahead. Did you want to say something?
No, I'm just listening. I don't know much about this topic.
Okay. Well, welcome. If you'd like
Thank
to,
you.
go ahead. Yeah. So anybody else? Richard.
Sure. Just real quick, I'll throw in that the Europa Clipper is it was launched 2024, and it's going to rendezvous with Europa in 2030. So we should sort of have some answers, hopefully, maybe good ones, as to what's under the ice on Europa.
Is this one actually going to dive into it?
Yes, well, I think it's going
No,
to
no,
release a
no.
probe that's going to melt its way through the thick ice to
Oh,
what they
really?
suspect is a subsurface ocean, and
Cool.
then release a probe to then, sort of swim around and figure out if
What,
there's any life under there. Yeah, so
Richard?
that
That's
should
a
be.
shit ton of
No, no,
energy to
no.
melt.
They're not
If
going to do that.
okay,
It's going to orbit
Right.
Jupiter, and
Mhm.
it is going to end up in Callisto. They're
So
not...
it's just going to it's going to remote sense the oceans or something. Is that
It's
what you're
going to
saying?
execute a series of flybys, and they're not doing the melting probe thing.
Oh, they're not doing it again. Oh, I thought they were doing.
that
Let
that,
me see,
that
because
melting
I just
probe
saw.
thing, Richard,
Yeah.
would take so much energy. The only way that I could imagine it would work would be to put a
Yeah. No,
small
that's right.
nuclear
No,
That
reactor
you're
was
on
right.
it.
the plan
You're
originally.
right.
Yeah.
You're right.
That's a
That
little
was the
bit of a
proposal.
dodgy bloody thing to be launching. I mean, I know it's
Launching,
been
yeah.
done.
Yeah.
Yeah, I think that there's a lot of energy to melt ice.
Okay.
About
Well.
planetary protection, they don't want to contaminate Europa with life forms from Earth even by mistake. So they are not
Oh.
going to touch it.
Okay.
Yeah, interesting. Well, Addie, if you're not in the field, you obviously do a lot of reading.
Oh, I cover the field, and I follow David Kipping a lot.
Ah, yeah, nice.
John,
Okay,
you were a physics professor, John, sir?
I was. Yeah, I'm a retired physics
You know
professor.
physics proves the existence of God, sir?
Oh, oh, here we go. Do I know that physics proves the existence of God? Is that what you're saying?
Yeah, that's
I just
right.
want to point out that Ben asked for this. Whatever's coming, Ben asked for it.
Yeah,
This is
So,
for you, Ben.
so I
I'm
imagine
Nibbles.
This
and
has
I,
your name on it.
I don't
I'm
think
Ben.
I want to go very
Ben.
far down this line, but I'm game for a little bit. I mean, I think if you're talking about Spinoza's God or something like that, I think I kind of have a warm spot in my heart for the idea that physics is God. It's kind of but I doubt that's what you're saying.
Yeah, no, it's like a deistic God, obviously, but you're an atheist, right? So you don't believe in any God.
Right. I'll just say my general take on it is that if you want to say we don't know where this came from, there had to have been a God. People have different ideas, right? That we're in a test tube. Some super race has created this experiment. We're part of this experiment. Whatever you want to say about we don't know where we came from, that's God. I'm down with that. But
Can I
my
ask a question?
well, let me just finish this quickly. My kind of quick take is that whatever created it created laws along with it. We know that because science is possible. Science works. When we reproduce conditions, we get the same result. So there are laws. We don't know what the laws are. We have things that we put out there as proto laws, possible laws, and they work pretty well. But I think the evidence is pretty clear that there are laws. And if you want to say that God created those laws, I'm down with that too. But having done all that, there's nothing for God to do in the universe today. If there is a God, if God is still with us, there's nothing for it to do but lie on the couch watching Seinfeld reruns. That's kind of my take on all of that.
It's a
Yes,
very
sir.
I
I
have
think
just
someone
specific
had a
the
theory,
question.
one,
John.
Ben. I just have the one question for I guess Wubby. You said physics proves God. Do you mean to say that physics proves the God of the King James Bible, the one who commits all
I
these
think he said no. I
atrocities?
think he was saying Diaz, but let's hear what he has to say.
Oh yeah, no. So God would just be like a necessary and immaterial mind that created the universe, whose nature is like absolute perfection, which just means that there would be like one fundamental property that's the essential property that constitutes the identity of God, and that property would have like infinitely many attributes. And so the argument would just be if the universe is emergent, then it's emergent from a mind. The universe is emergent, therefore it's
This is
emergent from a mind.
So
presuppositionalist stuff.
It's not
You're
well, it's
no.
presuppositionalist actually at all because it's not like
Platonism.
working with any preconditions, so it's not presuppositionalist. It's
So you're
actually using
doing
like sorry.
so you're just doing Platonism in 2025. That's awesome.
No, it has nothing to do with Platonism. I don't know if you're tracking. So again, it has to do with like quantum mechanics. I mean, particles are going to
There
be
it
waves
is.
in different types of fields.
Boom.
Oh,
So
so
excuse me,
so
it
hold
has
on,
no
everybody.
Platonism.
Hold on, everybody.
Anymore.
Wubby, this is not a direction I want to go, but I do want to give you a chance to kind of, maybe take 2 or 3 minutes to lay out your view, and then I think we will try to kind of move on.
Yeah, so the common belief among like a lot of laymen is that the universe is composed of particles, but quantum field theory doesn't really show that. Particles are actually waves in different types of fields that goes for all of the
Superpositions.
particles. So the reason for advocating for the view that everything is reducible to quantum fields is that many of the issues that particle interpretations have also apply to field interpretations. So one of the issues is that wave functional space is equivalent to the Fock space, which is the local algebraic instructions used in quantum field theory. And that would represent states as like particle configurations. And so the like two most powerful arguments against particles would also hold against a field interpretation. and in turn that indicates that like field interpretations can't really be like an available alternative to particle interpretations. So they have to like standard or fall together. So there's going to be like a lot of mathematical problems with saying that quantum fields are underlying objects, like the inability to
No,
assign
man.
Fock space, like other issues like spontaneous symmetry breaking. So in a lot of ways, like field and particle interpretations
Fields
sort
are
of like
not
have the
God.
same issues. And the
Take no,
problem is
everybody.
that under quantum
Take
mechanics,
another minute,
the important
Webby.
note is that like our macro reality is emergent from the underlying information, not fundamental objects that we call fields. So that supports the second premise of the argument that the universe is emergent. And also what else would support the second premise is the holographic principle, which is a theory that suggests like the entire three-dimensional universe is just 2D information.
You
So if
just
we just look at the
contradicted
first premise of
yourself.
the
But go on.
argument, we just make an abductive inference based on the laws of logic, and we say that
20 seconds.
No breaths.
Yeah. Okay.
Oh,
Okay.
It's
That's
amazing how
on, man.
fast people speak when they know that anybody can
yeah,
get in before
exactly. I
somebody's
was
going to
thinking the
speak.
same thing, and I feel, it's yeah, I don't know. It's too bad. We could continue to talk about it, but I think it's enough just to say this is what happens when you take a lot of kind of theories that are out there, speculation, et cetera, move them together, and then the giveaway is the certainty that this is the right interpretation of all of that, rather than saying, seems to me you could make the argument that, no, there's no argument being made here. He's telling us the way it is. And never mind all of the people who are actually doing that work, what they have to say about how sure they are about the things they're talking about. And it's yeah, I know it's too bad.
I wasn't the only one that noticed that the quantum mechanics was doing a lot of the heavy lifting there, right?
Yeah, but right. Well, an attempt to kind of glom on to the science thing, and that's fine.
Exactly.
I don't mind people believing what they want. Whoever moved him to the audience, we're probably about
Right
on the
on
verge
time.
of that anyway. And it's no offense. It's just that's not what we talk about in here. We've been joined by Steve and James, maybe in that order. Hey, Steve, did you want to say something?
Yeah, hi. Thanks for holding the space. Hello, everybody. I wanted to talk about the comet that just passed by
Yeah,
Mars, but I wanted to respond very quickly to the last guy. We love to talk about that on Sundays on Ask the Atheist.
that's right.
And John shows up a lot of the times. He is our physics guy. So if the guy is still here and he wants to come on Ask the Atheist, love to give you more time for that. They're great arguments. They're not. I don't believe they're proof, but they're great arguments. I came up though to
The
talk about
comet.
interstellar comet
Yeah.
3I Atlas. It passed by Mars
You're
on
too close to your mic. You're too close to your microphone, stranger.
and you've got a hot mic. You've got a hot mic. Thank you. And it just passed by Mars October 3rd because you guys were talking about gases and stuff. It's about 18 million miles or 29 million kilometers away. The event was observed by two European space agencies, Mars Orbiters, ExoMars, and Mars Express, which captured images of the comet as it passed the planet. It's now on its way to the sun.
It's not. That's the interesting thing.
Okay.
Yeah, no, thanks for bringing it up, Steve. There are a lot of fun things. I didn't know this until just this week, but it did. It came, I guess it came very close to Mars, came by Mars. It is now, I think, or right about now, at its closest approach to the sun, which is still much further away from the sun than we are. Most comets kind of go in, I mean, standard comets, unlike this one, go in closer to the sun than the Earth's orbit. This one is not. It's coming slightly inside Mars orbit, and then it's going to go back outside again and leave. And that's one really interesting thing about this one, is that it's just swinging by the sun, not even getting that close.
And it is currently the only known third interstellar comet that we know about. Yeah.
Right. It's the third, and I think the biggest and brightest that we've
Right.
ever seen. Yeah.
Exactly. So
Yeah.
thanks, John.
Yeah, thanks for bringing it up, Steve. I think it's really interesting. And the other interesting thing about it is this tail that is extending toward the sun. Evidently, the thing I read was suggesting that it's because the sun is heating up the one side, stuff is coming off that side, and because it's coming off with a slight ejection velocity, it's just moving toward the sun. I don't know what the actual explanation is, but that's a weird thing. Most comets don't have that. Probably having something to do with the fact that it's not getting close to the sun. Go ahead.
And one other thing, if I may, I believe it was either the History or the Science Channel. I was watching a repeat last night because I hadn't seen it. I had recorded it from last month. Um, they actually made a quote unquote comet in the lab, and it was about the size of maybe a bowling ball. She made it right there. She took dirt and she took some ammonia and she took dry ice, put it all together in the bag, and then it became the size of a bowling ball, and it was just there. And
And
then
shone a bright light on it.
yeah, exactly. She shone, or whatever you said, a bright heat light, and you could see the gases moving away from it as it was in her hand. So
Is this a YouTube, you're saying?
no, the history. It was either the
It's on
History
History
or the
Channel.
Science Channel, and it was first broadcast last month in September.
Well,
Yeah.
that's pretty fun. Yeah, thank you. Okay, we've lost a couple of other folks, I think. Let's see. Yeah, right. I don't see them around. So maybe we're winding down. We can do an after party, or somebody can if they want. I'm not going to open a room, but if there's a desire to do that, of course.
John, I was curious because Addy is kind of new here. In fact, I got to
Yeah.
add Addy to my list here. But he was saying some interesting things about
Absolutely. A valuable addition. Thanks for coming in, Addie. Go ahead, Ben.
I think Addie came once before. I think no.
Maybe so.
Well, somebody closed Ben's ears real quick, but he mentioned quantum superposition, and I was just curious if he had any thoughts on that topic, and I apologize for asking the question, which shall not be asked. Usually I ask the question that gets me booted from the room. That's my special skill.
Well, I don't remember Addie saying anything about it. Maybe did I miss something, Addie?
It's in the chat. We were talking about how
Oh, I
T-Rex,
see. Oh, I see. Okay.
we were talking about how T-Rex won the Nobel Prize, which you were not aware of, apparently. And people should be way more excited about the fact that T-Rex won the Nobel Prize than they are, I think.
Well, it seems like I thought usually one requirement for the Nobel Prize was that you be still living.
Yeah, exactly.
Well,
And you're a human being.
And that your arms are long enough to reach your knees. It definitely is a requirement. You've got to stick to the spirit of the original Nobel Prize.
No, you just have to do something that helps mankind, and clearly T-Rex have helped mankind ward off disease, if nothing else.
That's funny.
Nobody gets this, huh? So some people are still lost. They don't understand. That's funny.
Oh,
The thing about an audio app
yeah.
is that you can do puns. I mean, it wouldn't make any sense if you were on Facebook.
I never finished my story. The reason it came up is that we were talking about dinosaurs on the boat, and of course it's not just T-Rex. You got to have T-Rex and brontosauruses and pterodactyls.
All kinds of. It's a big ass boat.
Yeah, it's a big ass boat.
And if you read the text very carefully, the commandment is you have to take 7 pairs of every animal that is kosher. So
so was T-Rex kosher? Was it halal?
I don't know. It's an open question. We could open a room and talk about it if you want.
That would be
That's the side room. Is T-Rex halal or kosher?
That's right.
I think it's about the preparation.
Is the T-Rex that won the Nobel Prize halal? That should be the name of the room.
Really. Because
man.
it could start as halal and then it could eat a pig because it was hungry, and
I think
God knows what happens.
I am totally. I'm now. My juices are flowing to open a room. Was the Nobel Prize winning T-Rex halal or not?
Is the name of the title of the room anything other than John finally saw the light on quantum mechanics?
Yeah, 100% something.
100% talk about anything other than the fact. Yeah, got it.
Oh man, so many in jokes flying here. Okay, I think I'm moving toward closing this thing down. Even if
You're
there
gonna
isn't
let
an
this
after party room, I know
T-Rex won the
Benjamin.
Nobel Prize go without being like corrected?
Yeah, Larry says that T-Rex was an incredible English musical group. I was not a big Mark Bolan fan, so Larry and I may have to part ways on that one. But
T-Rex won the Nobel Prize for medicine,
yeah, and I
physiology,
don't think
whatever
they'd
that
even
is.
gotten a Grammy yet.
What is physiology anyway? And medicine or medicine?
You mean what's the prize?
No, what does physiology mean?
What
I haven't
is
been to a
physio?
I haven't been to a physiologist recently,
Oh, well,
and I'm wondering if that's maybe my problem.
that may be your problem. Yeah, I'm pretty sure you haven't been to a psychiatrist.
I
Physiologists
have done that.
study the human form, and if you turned up there, Benjamin, I'm not sure they'd recognize what they're dealing with.
You know, since I
Ah,
wasn't going to say anything because it wasn't germane to the conversation, but since we brought up physiology,
is
we
it
all
Benjamin now?
should know that the brain matures at about 25 years old. However, there was a recent study within the past 48 hours, I think from Australia, that says that emotional maturity doesn't happen till about 60 years old.
Oh, I think in my case, I'm still waiting.
That explains a lot.
But that is hot off the press, I think, from Australia.
And Steve, I just want to compliment you on saying germane.
Yeah.
Thank you. I would say my vocabulary is a tad better than average, John. Thank you.
Could you say my name, Steve, with the word Germain
Ben
buried in it?
Germain.
I feel like you
Germain.
could. There you go. I thought you could do it. That's a classic.
All right. Well, this conversation is really deteriorating. I am going to put it to an end.
I did like how John and Ben Germain used the phrase heavy lifting about 10 minutes ago. I like that.
Yeah. John, you have to resolve the Nobel Prize. It was won this year by T-Rex.
Okay. Well,
Um,
I think I think that should be another room. So, and so I just encourage everybody to look for, if not an after party of this room, look for Ben Germain's room if you want to talk about T-Rex and the Grammys
the
or
Nobel
the Nobel
Prize in
Prize. Yeah.
physiology or medicine.
Okay. All right. Well,
Did somebody
that's
at least put it in
with
the
those
chat?
tiny,
Nobody's
tiny
paying
little
attention.
hands somehow doing medicine. I'm trying to think about the surgery that you would do with those tiny little hands.
Thanks,
There you
John.
go.
Bye,
You
everybody.
have to have belief. You have to
Thanks,
have
Steve.
good intuition and a good sense of touch.
Okay, I'm going to play us out with another. I played us in today with a Kevin Gilbert song. Kevin Gilbert was the best musician of all time. Great singer, great songwriter, great recording engineer, great production guy, and died of autoerotic asphyxiation at much too young an age. But he
I've got
wrote
to
some
give
great
that
music.
shit up.
Yeah, so people really let this be a warning to you. And we'll see you next week.
Living by the printed page. It followed from the special theory of relativity that mass and energy are but different manifestations of the same thing.
I'd like to say thank you on behalf of the group and ourselves. I hope we pass the audition.